Welcome to the Deep Dive. Today, we are tackling a really fundamental engineering problem. It's something that, faces anyone who's serious about deploying custom AI. It's about moving from that academic, hey, this works in a lab success to practical daily usability.
Right, the real world.
Exactly. And our listener is looking specifically at automatic speech recognition systems, ASR, like Whisper. And they're asking just a brilliant set of questions.
Yeah, this is a great topic.
They know the basics, the standard metrics, but they want to know how to benchmark a system that truly works for their needs, which are, complex and domain-specific.
That's right, and that's the mission today. We are going to go far, far beyond the classic sort of simple metric, the word error rate, or WER.
Which everyone talks about.
Everyone talks about it, but we need to look at the parameters that define the ultimate utility of an ASR system. So we're diving into how you compare a stock general model against one of your own, a finely tuned, highly specialized model. And critically, how you make the case, both financially and technically, for running that custom model locally.
On consumer hardware, no less.
On consumer hardware versus relying on these expensive, often high latency cloud APIs.
It's a huge deal. I mean, Whisper's open source release, it just fundamentally changed the game. Suddenly we crossed this initial threshold.
It was a seismic shift.
We were getting remarkable accuracy, 2 to 4% WER on clean standard English audio?
With the large V3 models, yeah, that was really the proof of concept moment. It showed the whole architecture was sound.
Right.
But now you see it almost universally, the challenge has moved. It's not about achieving 90% accuracy anymore. It's about capturing that last 10%.
The part that actually matters.
The part that truly matters to a professional user. The reliability that, saves you time and saves you money. So our focus, it has to be on metrics that quantify efficiency, customization, and your deployment strategy.
Okay, so let's start with the classic word error rate. WER. It's the gold standard we always hear about.
It is.
We know what the letters stand for, but for you, the listener, could you break that down for us? What exactly does WER measure? And more importantly, what does it miss? What crucial aspects of real-world use does it just fail to capture?
Right. So at its core, WER it's a proportional measure. It's looking at transcription errors relative to the total number of words that were spoken in the original perfect transcript.
Okay, so it's a ratio.
It's a ratio, yeah. It's calculated based on something called the Levenshtein distance, which sounds complicated, but it just focuses on 3 core types of errors.
And what are those?
You've got substitutions, which is where one word is replaced by another. A classic example is weather, being transcribed as weather.
Happens all the time.
All the time. Then you have deletions, where a word is just completely missed. And finally, insertions, where the model kind of hallucinates a word that was never spoken. You add all 3 of those up, divide by the total number of words in the ground truth, and boom, that's your WE.
And the baseline, like we said, is phenomenal now. The stock large V3 models are sitting at, 3 to 5% WER on standard tests? So if a system is 95% accurate, why isn't that good enough? Why is that still insufficient for, say, high-volume professional dictation?
This is where we need to introduce a concept I call the usability cliff.
The usability cliff. I like that.
It's maybe the single most critical thing to realize for anyone deploying ASR in a practical setting. Because you see, the relationship between accuracy and how useful you perceive the system to be, it's not a straight line.
It's not linear.
It's not linear at all. It's exponential.
That's a fascinating claim. Can you walk us through that? What does that exponential relationship look like in practice?
Sure. Let's imagine 2 scenarios. System A is running at an 8% ER. System B is running at 5% ER.
Okay. So on paper, that's just a 3 percentage point gain. It seems small.
It seems small. But think about what that means. At 8% ER, you are correcting, on average, 8 words out of every 100. Now, if your average sentence has, 15 to 20 words.
You're almost guaranteed to have an error in every single sentence.
Every single sentence, maybe 2. So the user's cognitive load is constantly high. You're not reading to review your content. You're reading to find the errors.
You're hunting for mistakes. It's high mental friction, constant vigilance.
Exactly. Now, let's look at 5% ERR. The number of errors has dropped by nearly 40% in absolute terms.
Right.
You're now correcting, on average, 5 words per 100. You have just crossed the usability cliff. The user's mindset shifts completely. You go from correcting errors in every sentence to maybe correcting an error once every 2 or 3 sentences.
And the system goes from being just acceptable or, a little better than typing to being genuinely reliable.
That's the leap.
That changes the psychology entirely. I've personally felt that. When the error rate gets below that 5% line, the feeling changes from another thing to fix to, wow, this is actually saving me a ton of time.
And we can quantify that time saved. That's what a practical benchmark is. There are studies showing that correcting a transcript can take 4 to 7 times longer than the original dictation if the UR is above 10%.
4 to 7 times. That's incredible.
It's huge. By crossing that cliff down to 5%, the correction time just plummets. You might save 10 to 15 seconds for every minute of audio. For someone processing, say, 10 hours of audio a week.
That's hours of work saved.
Hours of work saved, all because your brain is no longer fighting that constant low-level friction.
Even at 5% ER, you still have 5 errors.
Yeah.
And it becomes a problem if those 5 errors are the wrong errors.
Yes.
And this brings us right to domain-specific accuracy, which is so vital for you if you're working with technical or specialized vocabulary.
This is WER's critical failing. It's a blunt instrument. WER treats a substitution of V for A with the exact same severity as it treats mistranscribing a technical proper noun like C-translate to.
Or a code-switched term, like the listener mentioned, mechalette.
Exactly. The first one, V for A, that's a trivial fix. Your brain almost does it automatically. But the second one, the technical term.
You have to stop.
You have to stop. You have to recall the context, maybe check the spelling, manually type in this very specific term. The cognitive effort is just disproportionately high for that one single error.
Let's stick with that code-switching example. You might be dictating in English, but you're constantly dropping in Hebrew phrases like mechalette.
Which means a grocery store or kiosk for context.
Right. A general stock ASR model will have a really high WER on those parts. Not because it's broken, but because, well, why? What is it seeing?
It sees those words as acoustic anomalies. General models are designed to find the statistically most probable English phonetic match. So if the model hears a Hebrew word, it tries to cram it into the English lexicon.
And you get garbled text.
You get something totally unfixable without the original context. So for you, the listener, benchmarking can't rely on a general test set like Common Voice. That's misleading.
You need a custom test set.
You need a custom test set.
Yeah.
15 minutes of audio that contains those exact technical terms, your acronyms, your code switch phrases. The true benchmark is the WER on that specific custom data.
So the goal of fine-tuning.
Yeah.
It isn't necessarily about getting a globally lower WER than large V3. It's about achieving 0 WER on the 5 or 10 critical terms that just ruin your daily workflow.
That is the strategic priority. A fine-tuned small model that scores, say, 7% WER overall, but correctly transcribes C-translate to and mechalette every single time.
That's infinitely more usable.
Infinitely more usable than a stock large model that scores 4% WER overall, but stumbles on those 2 key terms every time. The benchmark has to shift from broad accuracy to what we call contextual and domain accuracy.
That gives us a really clear picture of the accuracy side of the equation. Okay, let's pivot. If you're looking to deploy this custom model locally, on your own machine, accuracy is only half the battle. If a transcription takes longer than it took you to speak, the whole thing is pointless. So speed and latency are just crucial.
Absolutely. And speed is quantified using a metric called the real-time factor, or RTF.
RTF.
This is the fundamental performance metric for ASR inference. It's really simple. It's just the time taken to process the audio divided by the duration of the audio itself.
So an RTF of 1.0 means it takes 1 minute to transcribe 1 minute of audio. Real time.
Correct. And for streaming or near real-time dictation, you want your RTF values to be significantly below 1.0.
How far below?
Well, an RTF 0.5 means the transcription happens twice as fast as the speech occurred. For a genuinely seamless user experience where the text is appearing almost instantly as you speak, you want an RTF closer to 0.2 or 0.3.
And what can you, our listener, realistically expect to achieve with a modern consumer GPU? Let's say the AMD RX 7700 XT they mentioned.
Okay, so with that card, running a model like Whisper Medium, and this is key, with the right configuration, you should comfortably hit an RTF in the range of 0.4 to 0.6.
So 1.5 to 2.5 times faster than real time?
Exactly. That speed makes the system feel highly responsive. It's especially important when you're dealing with local batch processing of larger files, which we'll get into.
That brings us straight to the hardware dynamics. You mentioned earlier that people coming from the world of gaming into AI, they often misinterpret their performance metrics.
Yes, this is a huge one.
In gaming, if you see your GPU utilization spike to 100%, that's usually a bad sign. It means you have a bottleneck or maybe thermal throttling. Why is that rule completely inverted for ASR inference?
It's a critical distinction, and it all comes down to the nature of the workload. Gaming is a continuous sequential rendering pipeline. The GPU is constantly processing geometry, shading, textures, frame after frame after frame.
Constant stream of work.
A constant stream. So, sustained 100% utilization in gaming means the system is struggling. It can't keep up with the frame rate target.
And AI inference.
AI inference, in ASR in particular, is totally different. It's characterized by these short, incredibly intense bursts of calculation.
What kind of calculation?
Specifically, massive matrix multiplications. That's what it takes to run the model's forward pass. These calculations are incredibly parallelizable. So when the ASR model gets, say, a 5-second chunk of audio, it needs an immediate maximal compute effort to turn that chunk into text as fast as humanly possible.
So the model demands all available resources right now.
Exactly. Your GPU should spike to 100% utilization during those brief processing moments, the inference bursts, to minimize latency.
So if I'm watching my monitor, seeing it jump from near 0 to 100 and back down, that's a good thing.
That's a great thing. It confirms your hardware is being used optimally. In fact, if you failed to hit 100% during that burst, it would actually indicate a problem.
Like what?
It would mean the inference engine is inefficiently feeding the GPU, or there's some other software bottleneck, probably in the data transfer or kernel scheduling.
That clarity on utilization is so important. Okay, let's talk about the hard limit for deploying a model. VRAM capacity, video memory. This really determines which size of Whisper model you can even attempt to run.
VRAM capacity is the non-negotiable threshold. It's a hard wall. The model size dictates the raw memory it needs, and that's typically measured in 16-bit floating point precision, or FP16.
So what are we talking about for the common models?
Whisper Medium needs about 3.0 gigabytes of VRAM in FP16. Large V3, which is significantly bigger, jumps to about 6.0 gigs. So if your GPU has less memory than that, you simply can't load the model.
Unless
you use a critical technique, quantization.
Let's really expand on quantization. For local consumer deployment, this feels like the magic bullet. What is it, and what are the trade-offs we have to benchmark?
Quantization is the process of reducing the numerical precision of the model's weights and activations. So instead of using those 16-bit floating point numbers, FP16, we can move down to 8-bit integers, INT8, or even 4-bit integers, Q4.
And what does that do for us?
Two things. A massive memory reduction and often a big speed boost because integer math is just simpler and faster for the GPU to handle.
Let's focus on Q4. That's the most aggressive technique. What kind of savings are we talking about here?
Q4 quantization gives you roughly a 4x reduction in memory footprint.
4 times smaller.
4 times. So that 3.0 gigabyte Whisper Medium model, it shrinks to about 900 megabytes. And crucially, the large V3 model, which needed 6.0 gigs, becomes highly manageable at only 1.8 gigabytes.
So for you, the listener, with your 12 GB RX 7700 XT, that large V3 model is now easily within reach.
Easily, with plenty of memory left over for the OS and for these multi-model pipelines we'll talk about later.
This sounds like a pure win, but in AI, there are rarely pure wins. So what's the trade-off? If Q4 is 4 times smaller and faster, why would anyone ever use FP16?
And that is the critical benchmarking question that often gets skipped. The trade-off is a minor but measurable drop in accuracy. By crushing the precision of the model weights down to Q4, you're introducing these tiny numerical errors, a bit of noise into the calculation. This might result in, say, a 0.5 to 1.0 absolute percentage point increase in your WER.
Okay, so this loops back to our crossover accuracy benchmark. We have to consider this. If we fine-tune a small model and then we quantize it to Q4, does the fine-tuned Q4 small model still beat the accuracy of the stock FP16 medium model?
Precisely. That's the test. If your fine-tuned small model hits 6.0% ER in FP16, maybe quantization pushes it to 6.8%. You have to confirm that the slightly degraded accuracy is still above that usability cliff for your specialized words.
And is it usually worth it?
For 99% of local use cases, the speed and VRAM savings of Q4 are absolutely worth that small accuracy hit. But a rigorous benchmark must include the post-quantization performance test.
Beyond the model size itself, we also need to efficiently use the VRAM we have with something called batch size. How does optimizing that maximize performance?
Batch size is just the number of audio segments or chunks that you process simultaneously on the GPU. By increasing the batch size, you keep the GPU fully saturated.
What does that mean, saturated?
It means that when the GPU finishes processing one chunk of audio, there are other chunks immediately queued up and ready to go. You're eliminating those tiny idle gaps between the inference bursts.
We're aiming for maximum saturation during that processing window.
Correct. For your 12 GB GPU, you'll have to experiment. A medium model might allow a batch size of 4, maybe 8. A smaller model could potentially handle 8 or even 16.
And the benchmark is just trial and error.
It's iterative, yeah.
Oh.
Find the largest batch size that runs without causing an out-of-memory error or significantly increasing your latency. The optimal batch size maximizes your RTF, getting you closer to that ideal 0.4 speed.
Now, we have to address the elephant in the room for a lot of open source learners.
Mm-hmm.
Hardware compatibility. You're using AMD hardware powered by ROCm, which,
Sure.
let's be honest, historically it trails NVIDIA's CA ecosystem. How does this critical hardware choice impact the inference engine you choose and the benchmarks you get?
The AMD and ROCm compatibility is often the single biggest hurdle in deployment. It's just a fact. Most cutting-edge AI software is prototyped in PyTorch using CZ.
Right. It's the default.
It's the default. So when you move to ROCm, stability and performance often rely on these highly optimized third-party implementations that really know how to speak AMD's native language. So your benchmark has to evaluate the reliability of the entire software stack, not just the raw TFLOPs of GPU chip.
So which inference engines have actually navigated that ROCm landscape to deliver competitive performance?
We have a very clear data-driven hierarchy for the AMD ecosystem. At the top, Tier 1 is Faster Whisper using the C-Translate 2 backend.
The undisputed champion.
Undisputed. It's highly recommended because it bypasses so many of the performance bottlenecks that are inherent in these Python-based frameworks.
And you mentioned it's something like 3 to 4 times faster than the original PyTorch implementation. For this deep dive, we need to know why. What is C-Translate 2 doing under the hood to get that massive speed up?
It's an architectural game. C-Translate 2 is a performance-optimized C++ inference engine. So first, it massively reduces the overhead from things like Python's global interpreter lock, the GIL, and all the boilerplate code that just slows down the original PyTorch version.
Okay, so it's leaner.
It's much leaner. But second, and this is the most important part for speed, C-Translate 2 uses these highly specialized, hand-optimized kernels for the common deep learning operations.
Specifically the matrix multiplications.
Specifically the massive matrix multiplications, the GMs, is providing custom instructions that are tailored for efficient execution on the GPU's specific architecture.
So it's speaking the GPU's language much more fluently than general PyTorch can.
Precisely. These kernels are built to maximize memory access patterns and use the GPU's tensor cores, or the AMD equivalent, far more efficiently. It also handles loading and converting quantized models Q4 INT8 natively in C++ tech, which makes the whole memory transfer and computation flow incredibly streamlined and fast.
And that's where the 3x to 4x RTF improvement comes from.
That's where it comes from.
That distinction is just crucial. It means performance isn't just about the chip. It's about how effectively the software engine can instruct that chip. So what are the fallback options?
In Tier 2, we have the original Whisper implementation running on PyTorch with ROCm. It's functional, but it's slow. A benchmark here really only serves to show you why you need C-Translate 2.
A baseline to compare against.
Exactly. Also in Tier 2 is OwnNNX runtime. It offers great cross-platform portability, but its ROCm provider is often less aggressively optimized than C-Translate 2 and can sometimes be a real headache to set up.
And what should you explicitly avoid for GPU inference?
For GPU production use, you should avoid Whisper.cpp. This is Tier 3.
Which is counterintuitive because Whisper.cpp has a huge reputation.
It does, and Whisper.cpp is phenomenal, absolutely Tier 1 for CPU-only inference. It's a masterclass in C++ CPU optimization, but its support for HIP and ROCm on the GPU side is still experimental and, frankly, unstable.
What happens when you try to use it?
Users frequently report these silent fallbacks, where they think they're running on the GPU, but the job is actually being handed back to the CPU without any warning.
So your RTF just tanks, and you're left wondering why your powerful GPU seems so slow.
Exactly. It's confusing and degrades performance severely.
That is a phenomenal summary of the performance stack. It confirms that the true benchmark for local deployment isn't the raw speed of your chip.
Yeah.
It's the RTF achieved by the C-Translate 2 engine using Q4 quantization. That's the magic combination.
It is. It's the only stack that currently lets you compete with commercial offerings in terms of raw latency if you're not on NVIDIA hardware.
Okay, this brings us to the core strategic dilemma for you, our listener.
Mm-hmm.
The effort required for fine-tuning. If the stock media model is already getting, let's say, 7% ER, is it worth the time, the effort, the compute cost to fine-tune a smaller model, like small or even tiny?
This is where we uncover this massive strategic advantage of fine-tuning for local use. We call it the fine-tuning crossover effect.
Okay.
And the bottom line is this. For deployment on resource-constrained local hardware, fine-tuning smaller models isn't just a practical idea, it is generally the optimal strategy.
Why? Why does a smaller model benefit disproportionately more from fine-tuning than a larger one?
It comes down to two things: capacity limitation and generalization. The large models, like large V3, have billions of parameters.
That's massive capacity.
Right. They have the capacity to memorize and generalize across vast amounts of diverse speech, accents, vocabulary, you name it. A small model, on the other hand, has far fewer parameters. It has to generalize broadly just to cover all types of speech.
It's spread thin.
It's spread thin. So when you fine-tune that small model on, say, 15 hours of your specific voice, your specific accent, and your technical jargon, you're essentially telling the model to dedicate 100% of its limited capacity to that one specific domain.
You're making the small model forget the 90% of general speech it learned that's irrelevant to you, and instead concentrate all its resources on the 10% that actually matters.
That's it, exactly. And because of that, the relative WER reduction you get on small models is far, far greater. A 10-hour fine-tuning pass on a large model might reduce its 5% WER to 4%.
20% relative improvement, one absolute point.
Right, but that same 10 hours of training on a small model that started at 10% WER, that might drop it to 6.5%.
A 35% relative improvement, 3.5 absolute points.
That is the crossover. The fine-tuned small model now performs better than the stock medium model, but only for your specific use case. And because the small model requires so much less VRAM and compute,
It runs much faster locally.
it achieves the usability threshold. It gets you below that 8% ER cliff, while offering a superior RTF and zero ongoing operational cost. That is the definition of a successful fine-tune benchmark.
So now let's do the deep value benchmarking that you asked for. The cost comparison. Local fine-tune versus a cloud API. We need to find the financial break-even point.
This requires some clear math. Let's make an assumption. You're a heavy user, maybe dictating or transcribing 2 hours of audio every day, 5 days a week.
Okay, so that's about 40 hours a month, 2,400 minutes.
2,400 minutes per month. Now, on the cloud side, let's use OpenAI's standard Whisper API. That costs about 0.0006 per minute.
So 2,400 minutes times 0.006.
Gives us an ongoing monthly cost of $14.40. Now, that might sound low.
Right.
And if you factor in inevitable usage bursts or using the more expensive large V3 model or other premium APIs, that cost easily climbs to $20, $30 a month.
And if you're a professional using this heavily, say 5,000 minutes a month, the cost is closer to $50.
$50 a month, easily. So let's conservatively anchor that ongoing cloud cost at $30 per month for heavy professional use.
Okay, $30 a month. Now what's the local investment?
We'll use your target hardware, an AMD RX 7700 XT. Right now, that's priced around $400 USD. That's a one-time sunk cost.
Right.
We also have to factor in the fine-tuning cost. Using cloud compute for, say, 10 hours of fine-tuning on a small model might cost you roughly $50 to $100, depending on the instance you rent.
So let's estimate the total upfront cost GPU plus the fine-tuning compute at around $500.
$500 up front.
So we have a $500 upfront cost for the local system versus an ongoing $30 per month for the cloud subscription.
And the break-even point is therefore around 16 to 17 months.
$500 divided by $30.
Exactly. After about 17 months, the local system becomes financially superior. It gives you zero ongoing operational cost, much lower latency, superior domain accuracy, and on top of all that, complete data privacy and offline capability.
That ROI analysis is absolutely compelling. If you anticipate using this system for more than, say, a year and a half, or if you have high volume or sensitive data, the local fine-tune model is the clear strategic winner.
Absolutely. The marginal accuracy advantage of the stock cloud model, that 3-5% ER, it just doesn't justify the practical drawbacks compared to your local fine-tune hitting 6-8% EIRR on your custom data.
And it's important to remember.
And, sorry to jump in, but remember that accuracy gap only applies to general audio. On your specialized technical data, your local fine-tune will benchmark better than the cloud API.
So you're paying more for an inferior result on the data you care about most.
That's the kicker.
Okay, let's talk about the parameters that influence the success of that fine-tuning. It's not just about dumping audio files into a folder. How much data do you really need?
Training volume is key. For solid domain adaptation, we recommend collecting, and this is important, meticulously transcribing 10 to 20 hours of high-quality audio data.
10 to 20 hours.
That range gives the model enough exposure to your accent, your rhythm, your vocabulary to successfully retune its parameters. If you're targeting that 20 to 40% relative WER reduction we talked about.
For the crossover effect.
For the crossover effect, yeah. 10 to 20 hours is the minimum threshold you should aim for.
And when you say high quality, let's get technical. What defines audio quality in the ASR world?
Quality is defined by the signal-to-noise ratio, or SNR. It's a fundamental concept in audio engineering. SNR measures the power of the desired audio signal, your voice, relative to the power of the background noise.
So for you, the listener, what does an ideal SNR look like in practical terms?
We aim for an SNR of 20 dB or better. What that means is the power of your voice is 100 times stronger than the background noise.
And what happens if your training data drops down to, say, 10 dB SNR, which is common for, a bad microphone or a noisy office?
At 10 dB, the signal power is only 10 times the noise power. And training on that low-quality data it's disastrous.
Why?
A general rule of thumb is 10 hours of high-quality 20-plus dB data will almost always outperform 50 hours of noisy 10 dB data. When you train on noisy data, the model learns the noise itself as part of your speech signature.
So it learns degraded representations.
Exactly. It leads to inconsistent quality and higher WERs when the model eventually encounters clean audio. You absolutely must ensure your training set is pristine.
Finally, let's talk about audio length. Whisper has that famous 30-second architectural window. How should you prepare your audio chunks for optimal fine-tuning?
While Whisper can technically handle shorter segments, the optimal training chunks are between 10 and 30 seconds long.
Not shorter.
Shorter snippets under 10 seconds, they often lack the necessary contextual information, and forcing alignment on segments over 30 seconds requires complex padding and can be inefficient.
So why is that 10 to 30 second window the sweet spot?
Because that length captures the natural flow, the prosody, and the rhythm of human speech. Those are essential for the model to learn things like accurate punctuation, capitalization, and even contextual disambiguation.
Fragmented audio just teaches sounds.
It teaches isolated phonemes. Longer chunks teach the model how you, the speaker, actually structure your thoughts.
We have successfully benchmarked pure accuracy with WER and speed with RTF, VRAM, and the right engine. But a truly usable professional transcript is so much more than just a stream of correct words.
Oh, absolutely.
It needs punctuation. It needs paragraph breaks. It needs to know who is speaking. These structural and usability features, they feel like the next frontier. So how do we benchmark these vital bells and whistles?
This is where the industry is investing heavily now, post-Whisper. We're moving beyond raw ASR and into what we call semantic and structural accuracy. And these features are almost never handled by the ASR core model alone. They require a multi-model orchestration. So the true benchmark becomes the system's ability to maintain that structural integrity while still respecting your latency constraints.
Let's tackle punctuation first. You hinted before that punctuation is often more about a user's written style than their spoken style. So how can you benchmark and achieve personalized punctuation?
It's a multi-layered problem. The integrated ASR models, like Whisper, they try to learn punctuation from acoustic cues, pauses, changes in intonation, rhythm.
But that's inconsistent.
Very inconsistent. I mean, I might pause dramatically for effect, but I wouldn't put a comma there in writing. A truly personalized system has to reflect your typical writing conventions.
And your recommended solution for this involves a separate model.
Yes. Often a lightweight sequence-to-sequence model that's optimized just for punctuation restoration. And the breakthrough strategy here is to benchmark and train this model not just on your speech transcripts, but on a massive corpus of your actual written work.
Emails, documents, reports.
Exactly. Maybe 50,000 to 100,000 words of your own writing.
Training the punctuation model on my written archive. Why is that so much better?
Because it captures your stylistic consistency. If you have an affinity for using the M-dash, for example, or if you consistently use semicolons, or you prefer these long, verbose comma structures, the written corpus teaches the punctuation model those specific patterns.
And it does that independently of how inconsistent your physical pauses might be when you're speaking.
Precisely. The benchmark here isn't just the presence or absence of a comma. It's stylistic consistency relative to your formal writing.
That's a powerful insight.
Yeah.
A good benchmark should assess how often the output punctuation matches your known writing conventions on a held-out written test set. Okay, what about structural benchmarking? Paragraphs, section breaks. A long transcription with no breaks is almost unusable.
It's a wall of text, and paragraph and section detection is highly challenging for ASR models because these breaks rely on implicit semantic shifts, not explicit acoustic cues.
The speaker doesn't usually say new paragraph.
Right. So current research and deployment rely heavily on sophisticated post-processing models, and this often involves large language models, LLMs.
How does an LLM help with paragraphing?
The raw transcript, that stream of words from the ASR core, is fed into a specialized LLM, and that LLM has been instructed or fine-tuned to identify topical coherence and semantic shifts.
What?
So if you've just spent 2 minutes detailing the technical specs of a GPU, and then you suddenly shift to discussing the financial break-even point, the LLM recognizes that transition as an implied paragraph or section break.
So the benchmark for structural integrity is the system's ability to identify these semantic boundaries accurately based on human standards for logical flow.
But doesn't adding an LLM to the pipeline massively increase the latency?
It absolutely does, and this is the core challenge of multi-model orchestration. You can't just benchmark the ASR core anymore. You have to benchmark the cumulative latency of the whole chain.
So if the ASR core takes 30 seconds to process a minute of audio and RTF of 0.5.
And the LLM post-processing takes another 15 seconds, your effective RTF is now closer to 0.75. And you, the user, have to decide if the improved usability from the paragraphing is worth that added latency.
And finally, diarization, identifying who said what. This is non-negotiable for meetings, for interviews. Diarization is essential, yes. There are tools like pianote.audio that offer extremely high accuracy for speaker recognition. But again, the challenge isn't the individual model's accuracy, it's the integration and the latency.
How so?
Diarization often requires pre-processing the entire audio file to extract voice characteristics and then aligning those characteristics with the text output. It's another step, another model to run.
So a modern professional speech-to-text application isn't one model. It's a pipeline of at least 4 models running either sequentially or in parallel.
That is the architectural reality. You start with voice activity detection, VAD, to filter out silence and noise, which improves the ASR input quality.
Step 1.
That then feeds into the ASR core, your faster whisper Q4 fine-tuned small model. The text from that goes to the punctuation model and concurrently to the diarization model. And finally, maybe it all goes through an LLM for structural correction. Your benchmark has to account for the cumulative resource demands of this whole pipeline working in harmony on your hardware.
This orchestration challenge, it must have a direct impact on the architecture choice. Batch processing versus live streaming. Which one delivers better structural accuracy?
Architecturally, batch processing consistently yields superior contextual and structural results.
Why is that?
In batch mode, the system has the entire audio file available from the start. This allows for global optimization. The ASR model can use bidirectional context. It can look backward and forward in the audio.
It has the full picture.
The full picture. The VAD can be more precise, and the post-processing models, like the LLM and diarization, can execute these sophisticated multi-pass algorithms without any real-time pressure.
Whereas in live streaming, the model is just reacting instantaneously. It has to make these irreversible decisions on the fly.
Precisely. Streaming transcription operates under fixed, strict latency ceilings. You simply cannot wait for the full context. This forces the model to use simpler inference settings, and it limits the sophistication of the post-processing.
And the end result is?
Often lower accuracy on boundary words and, critically, poor structural integrity. So if accuracy and structure are paramount for you, your benchmark should absolutely be conducted in the batch context.
We have achieved a genuine deep dive here. We've navigated the technical and the strategic metrics, moving way past WER and RTF, detailing the stack you need for AMD hardware, calculating the break-even point for local fine-tuning, and identifying the structural needs of a professional workflow. The lesson is just so clear. Your deployment success hinges entirely on prioritizing strategic optimization over just grabbing the biggest brute force model.
Let's crystallize the 3 most important benchmarks for anyone building their own optimized, personalized ASR system, whether you're a learner or an enterprise developer.
Let's do it.
First, RTF and efficiency. Your number one priority is minimizing latency and maximizing your hardware utilization. This means you have to use an optimized inference engine like faster Whisper, couple it with aggressive quantization like Q4, and run it on optimal batch sizes. The goal is to hit an RTF of 0.5 or better.
Number one.
Speed. Second, crossover accuracy. Do not rely on general test sets. Benchmark your Q4 fine-tuned small model against the stock FP16 medium model on your own personal domain-specific held-out test set. If you successfully cross that accuracy gap for your critical vocabulary, the fine-tuning effort was justified. And remember to account for that minor accuracy hit from the Q4 quantization.
Number two, targeted accuracy.
And third, usability. The final system must benchmark highly against your specific pain points. Reliable handling of your code switching, your specialized vocabulary, and your stylistic structural elements. Even if that means integrating a multi-model pipeline that increases the overall latency just a little bit.
And we'll leave you with a final provocative thought to mull over. Our entire discussion today has been about optimizing technology to reduce the error rate to the bare minimum 5%, 4%, even 3%. Yet we know that in the most mission-critical fields, legal proceedings, medical dictation, air traffic control, where cost is secondary to perfection, those systems still mandate a human-in-the-loop QA step for final sign-off. So if the global ceiling of ASR still requires human review to cover that final 1% of ambiguity, will we ever truly cross the human-level threshold? Or is that residual error, that final inescapable cognitive gap, something we must always design our professional workflows around, shifting the focus from perfect transcription to perfect low-latency correction? Think about that as you design your system.